Okay, and so now we're going to look at part 2 of combining the equations, and this is going to produce our final equation. There are 4 sort of common acceleration equations, and you know we've already got the v equals at plus v naught. We've got the delta x equals 1/2 v plus v naught t. We just derived a formula by combining, substituting the v to come up with a new equation that was delta x is 1/2 at squared plus v naught t. Now what we're going to do in this one is I'm going to substitute for the time in this equation. Now in order for me to substitute for time, I'm going to need to clean this one up over here and to solve for t. So I'm not going to do the algebra, I'm just going to give you the final answer. That's going to be v minus v naught divided by a. And I'm going to take that and I'm going to bring it over and substitute it for that time. Now obviously when I do that, this is going to be our first equation in which there is no time. Both of these equations have time, and the last equation, delta x is 1/2 at squared plus v naught t, that was filled with t. This is going to be our first equation in which there is no time. So obviously an equation that would be very useful if you didn't know the time and you didn't care what the time was for the event. Instead you only wanted to know about the other 4 variables. So let's take a look at what happens when we make that substitution. We get delta x is equal to, we've got a 1/2 here, we have v plus v naught, and now we're substituting for t, so we're going to end up with v minus v naught over a. So I'd like to do a few things to sort of clean this situation up. Let's first of all multiply by 2. That's going to bring a 2 to the top over here, 2 delta x. And let's also multiply by a, because I have an a on the bottom over here and I want to bring that up over to the other side. So I'm going to get 2 times a delta x, and that is going to be equal to v plus v naught times v minus v naught. Now this is a polynomial, and you should recognize that you would use FOIL essentially, the first, the outer, the inner, and the last to come up with it. But this is like a special version of FOIL, because take a look at what you have. You have something plus the variable and something minus the same property or variable. So what's going to end up happening is when we do the outer, we're going to get minus, because of this minus sign, we'll get minus v naught v, and then on the inner term we're going to get plus v naught v. Those two things are going to cancel each other out. So that in the end all we really get is the first, which is v squared, and the last, which is minus v naught squared. And generally the form of this equation that you're going to see when you're looking at data booklet is it's solved for v. So you can see if I were to solve for v, I would just add the v naught squared over to the other side, and I would end up with this final equation. V squared is equal to v naught squared plus 2a delta x. And that is our fourth and final equation. So just like with all the other equations, there are 4 variables: v, v naught, a, and delta x, or d. So let's take a look at a couple of examples. With 4 variables, there are 4 things to solve for. We'll just look at 2 examples. We'll solve for 2 of those things. In this example, how far will I travel if I accelerate from 5 meters per second to 15 meters per second at a uniform rate of 2.5 meters per second squared? So let's just go in order each of the 3 things I was given. V naught, 5.0 meters per second. The final velocity, 15 meters per second, and I did this at a uniform acceleration of 2.5 meters per second squared, and I am looking for delta x. I don't know the time, and I don't care about the time. Okay, I could use these previous 2 equations back up here to solve for this problem. I have v, v naught, and a. That means I could solve for the time, then take that time, just like I did with the substitution, and substitute that in over here, and then solve for delta x. The power of this equation is, rather than solving for a variable that I don't care about and then using that to solve for the real variable, which in this case is delta x, this equation is going to allow me to go directly to the answer without having to worry about that middleman. And just to remind you, this equation will be given to you on the data booklet. So v squared is equal to v naught squared plus 2a delta x. And I want to solve for delta x, so we'll do that in a couple of steps. V squared minus v naught squared equal to 2a delta x. I just moved the v naught over to the other side, and now finally v squared minus v naught squared. I'll divide by 2a, and when I divide by 2a, I will end up with my delta x by itself. And so with the delta x by itself, on the other side now we can start plugging in numbers. I have v, which is 15 squared minus 5. When I plug in the numbers, I tend to drop off the significant figures. I can always go back here to figure it out in the end. But just to make the math a little easier, a little cleaner, I tend to not write the 5.0. You certainly can, though. There's nothing wrong with doing that. And we're going to divide that by 2. This is like really important. People oftentimes forget to put that 2 in there, and so obviously they end up with an answer that's twice as big as it should be. 2 times 2.5. And so at this point we can go to the calculator. So we have 15 squared minus 5 squared equals, divided by 2 parentheses 2.5. That didn't work out. 15 squared minus 5 squared equals, divided by 2 divided by 2.5. Okay, so the answer should have been 40. So my delta x is 40 meters. Okay. Last example for the combination of equations. And in this one, we're going to have Manny travel 15 meters, I should say, while accelerating at a constant 1.5 meters per second squared. And if his initial velocity was 3.0, what was his final velocity? So let's go through the given information in order. We'll start off with 15 meters, which is clearly the delta x. His acceleration, a, was 1.5 meters per second squared with an initial velocity of 3.0 meters per second, and we are looking for v. Alright, this one's actually a little easier because you can see we won't have to solve for anything. I tend to find that I leave the equation like this. Obviously I could put a square root symbol over the whole thing. I really don't like the radical sign if I can avoid it. So I'm just going to leave this as v squared for right now, and we'll go ahead and plug everything in on the other side. We had 3 squared plus 2 times 1.5 times the displacement of 15. So going to the calculator, 3 squared plus 2 times 1.5 times 15, that's 54. And then now we need to take the square root of that, so I can say that v finally is the square root of 54. Sorry, square root of 54, which is 7.348. And if I look back here, I've got 3 significant figures, 2 and 2, so I'm going to have to leave that as 7.3 meters per second. And that's one of the possible examples. Obviously, besides solving for delta x or solving for v, I could have solved for v naught, or I could have solved for the acceleration, depending on what I was given and what I was looking for.